Welcome back. And now James Pascaleff is going to be from University of Illinois, Urbana-Champaign. He's going to be speaking to us about the Floer-theoretic nature of canonical bases and his joint work with Yankee and Nick.
Hello. All right, thank you. Yes, thank you for the introduction, Renato, and thank you for having me here in Rio. It's been an amazing week. So, yes, I'm going to talk about a joint project with Yankee Lakili and Nick Sheridan that we have worked on for a long time, and want to show you a picture that comes out of it that I think is very pretty, that relates to this notion of a canonical basis, which is a notion that comes from representation theory. So the main topics for today are going to be things like equivariant structures in Floer theory and an application to representation theory. Okay, so maybe a little motivation or kind of orientation to this question. So one thing we're interested in the general philosophy of homological mirror symmetry is understanding the counterpart of any structure that you can see in algebraic geometry. So one structure you can see in algebraic geometry would be a group action. So a group action on what I call the B side, that's the algebraic geometry side, so you would have a variety X, and then an algebraic action of a algebraic group G. And you want to kind of understand, what is the mirror of this situation? I mean, another way to think about it, if you want to think about this as a space, you could, of course, form the stack X mod G. And you could ask, what is the mirror of this equivariant geometry? That's kind of the question. So it's some kind of, what is the mirror of the equivariant, the G equivariant geometry of X? And this has some interesting connections. I mean, when you start thinking about things like this, there's lots of interesting connections for this problem to, some connections that are of current interest, I think. So connections to questions in, geometric invariant theory and, the theory of window equivalences and so on. They lead one to try to understand mirror symmetry for things like this. I mean, that's one thing you might be interested in. Well, I'm not going to say much about this angle, but I'm just going to more talk about just the basic question. What is the mirror of this type of structure? And I'm going to present an answer, or something of an answer, and I'm going to see that that answer has some connection to a problem in representation theory. Okay. One thing I want to emphasize, because it's maybe not completely apparent, is that there are a number of cases where this kind of equivariance is well understood. So some cases that are, I think, fundamentally simpler than what I'm going to talk about are I should say cases that are sometimes understood. So cases that are, you could look at it, say, for G is finite. That's one thing you could assume, and then try to do the theory there. Another thing you could assume is that G is abelian. So, for example, G could be a torus. And in these cases, there's often some kind of explanation that if you take the mirror of this type of group action, it corresponds to some kind of covering space of the mirror. So in other words, if my X is mirror to some X check, then this equivariant geometry may be mirror to a covering space of X. So it's just the ordinary theory of covering spaces. So somehow this extra equivariant structure, it sort of separates out different parts of the geometry according to, say, the weights of the action of this torus, and that way of separating things out corresponds to taking covering space. So you can see this, for example, in mirror symmetry for toric varieties. If you look at the works of, say, Fang, Lu, Troyman, Zaslow, supplemented by work of Kuwagaki and others, you can see this very, very clearly, that if you want to say study, it's a mirror of a toric variety, you'll get basically what we would now call partially wrapped Fukaya category on the cotangent bundle of the torus. And if you want to study the T equivariant geometry of that toric variety, you get essentially the same thing on the covering space of the torus. So the cotangent bundle of Rn instead of the cotangent bundle of the torus. Okay, so this is so basically this kind of cases you can study using basic topology covering spaces. But the thing I actually want to talk about is where G is really it's positive dimensional non-abelian algebraic group. So to go to the non-abelian case, something new is needed. And basically the new thing we're going to use is this theory of equivariant Lagrangians. That originates in the work of Seidel and Solomon. So, okay, so this point will be one of the main things I'll try to explain in this lecture. Okay. All right. Any questions or comments so far? All right. So maybe I'll want to say something. So yes, as I say, in a minute I will, explain what this theory is. One thing you might ask is, okay, you can sort of set up some kind of theory like that. And you might ask, what is it good for? Is there some application that shows you that you really have a reasonable theory, that this is really the right way of looking at things? So that's the application I want to talk about, which has to do with canonical bases. So maybe I'll just say a little bit about that. And I plead that I'm not an expert representation theorist, so this is so I can't say that I'm going to give a complete description of what this concept is, but here's what it means to me. So the basic idea is that you have a representation of a group. So you have a group G, which acts on a vector space V, and you might want to know, okay, is there some kind of preferred basis for this vector space V? And you would say to yourself, of course, there isn't, because the whole point of representation theory is that this object has a big symmetry acting. You pick some vector here, well, it gets moved around. There's no canonical vector you could write down because they get permuted by the group action. So that's not really what canonical basis means. It's not canonical in some kind of sense of abstract category theory or functoriality or something like that. It really just means that you have a nice picture of this basis. And nice could mean various things. So usually speaking, it's a basis here. But this sort of canonical basis, one thing to understand is that it's usually sort of meaningful with respect to a presentation of the group in a certain way. So often in this talk, I'll use frac G to denote the Lie algebra of G. I'll sometimes elide the difference between small g and big G. Really, the results are all about little g. I'll just say that. So my G, this one, I'm actually now going to restrict to semi-simple group. And I'm working over the complex numbers always. So there's, if you take a course in Lie algebras, you'll learn that a semi-simple Lie algebra, over the complex numbers can be presented to you in a very nice way. So the general idea is that this G contains an abelian subalgebra, so they call it Cartan subalgebra. And then this Cartan subalgebra acts on G by the adjoint action, and you can sort of diagonalize that action. And then you get a very nice, and that gives you the theory of weights. And you get, basically, you get a root system from this. So I'll do the Sl3 case. So in the Sl3 case, it looks like this. So here's H. So this is Sl3. So Sl3, if you're not up on this, this is 3 by 3 traceless matrices. H is going to be the diagonal matrices. This is one choice of H. And then, so what happens is, this traceless 3 by 3 matrices is an 8-dimensional vector space. And then it sort of breaks up this way. You have the traceless matrices sitting here, and then you have one basis element at each of these weights. So this is a weight diagram for the adjoint representation of Sl3. Okay. So these are your basic weights here. Okay, so alpha 1, alpha 2. Okay. So this is, and then you choose, there's more choices, so I choose a set of positive roots and so on. Basically, you present your Lie algebra in a very nice way. So you have this Cartan algebra, and then this is called Chevrolet-Serre presentation of the Lie algebra. So you have the Cartan, and you have generators for these simple roots, and then there's a set of relations that they satisfy, and this generators modulo those relations gives you G. And so I like to mention this because this, the thing you see, the nice basis you see is really something where it's sort of compatible with this presentation of the Lie algebra in a nice way. Okay. And so the basis should have some kind of nice properties. So it should have, maybe I'll be a little bit vague here, but some nice form with respect to action of and Fi. Might be difficult to say what nice means. Another typical feature of these canonical bases in representation theory is that they have some geometric origin. If I'm not mistaken, a lot of these constructions, I think, in one of these main constructions is due to Lustig, where it uses geometry of Nakajima-Quiver varieties. There's other constructions that use things like quantum groups. Another construction that I kind of am a fan of is there's a construction that uses something called the affine Grassmannian, which is an infinite dimensional variety. So e.g., this is Mirkovich-Volonin. Basis uses geometry of something called the affine Grassmannian of the Langlands dual group to G. Okay. So they often have some really sophisticated geometry that goes into these bases. I mean, that's what I want to say. And kind of the point of my talk, a point of this application is that maybe it's just complementing these works that already exist, is that there's another underlying geometry that gives you a canonical basis, which is Floer-theoretic in nature. Okay, I believe, and we have results for Sl3. Okay. Okay, cool, and it has to do with. So today we'll do some Floer theory in sort of the ordinary flag variety. that will be another source. Okay. And maybe just to spell out, maybe to avoid delaying the punchline, I'll just try to spell out now what that ultimately looks like. So this will be my semi-simple Lie algebra. And today the actual results are going to be for the case of Sl3. So the irreducible representations of this thing are indexed by what are called dominant integral weights. And then, as I said, corresponding to that, there's an irreducible representation. Of highest weight lambda. And then I'm going to consider a certain Weinstein manifold, which I'm going to call R. This is actually going to be an open set in flag variety. Let's say G mod B. It's known as, sometimes this thing, we call this thing the Richardson variety. And what's going to happen? I'm going to have, so this is actually going to be a Weinstein manifold. I'm going to look at some non-compact Lagrangians in here, and I'm going to compute their Floer homology. So I'm going to consider Rapp Floer cohomology in degree 0 of certain Lagrangians. Okay, they're going to have a subscript. These Lagrangians are going to have a subscript that is this lambda. And what I'm going to find that actually this vector space has an action of that Lie algebra. So there's actually going to be a Lie algebra action of G on this vector space. And this vector space actually is going to be, the way I'm setting it up, I would like to make this sharper, but the way I'm setting it up, this will contain V lambda. It'll actually, this is a representation. It has a sub-representation, which is this one. And this G is actually going to have also itself a geometric interpretation in that it's going to be interpreted as a subspace of the degree 1 symplectic cohomology of R. Okay. So you see here sort of the diagram. Oh, and then one more thing, of course. This thing is going to have a basis. Yeah. Excuse me. Thank you. And this guy is going to have a basis. So this was vector space. Sorry, I need the eraser. So this is going to have some basis. Okay, probably I need to introduce more notation, but there's going to be a subset. Okay, there's going to be a certain discrete set I'll call gamma sub lambda, which indexes the basis elements. This is my canonical basis. And what is this set gamma sub lambda? It's actually a subset of another set I call B of Z. This is the set of integral points in a certain integral affine manifold. So this is integral points in an integral affine manifold. And these integral points, in fact, well, okay, maybe my notation isn't really distinguishing, but there'll be these integral points in an integral affine manifold, which are also in bijection with certain generators of this thing, so certain Hamiltonian chords. Okay. So, excuse me? No. Yeah, I knew that was going to be a problem. All right. this b, I'm not going to change that b. So let's just call this y. So y is going to be the base of the SYZ vibration today. Okay. Let's call it y. All right. Thank you. More questions or comments? This is really just setting it up, and now I have to explain all this stuff. So, but let's see. All right. Okay, cool. What are the properties of the gammas that make them special? Right. Well, yeah, good question. I mean, so I think the point is that this is really the thing that I think is interesting. That it's like somehow, well, first of all, that, it comes from geometry in some way. I mean, I think actually the interest here is that, yeah, so this thing mixes, sort of geometry and algebra in kind of in a somewhat complicated way. So the point is that several things have to line up. Like it's not really, it's not really automatic to get this picture, because I mean I could take, this vector space and I would get maybe Floer theory tells me I have some basis for it. But I also need to have an action so that some subset of that basis gives me a basis for this representation. So somehow the fact that these things are lining up tells you that something meaningful is happening. I mean, I think it's difficult exactly to characterize these canonical bases, and you'd like them to be canonical in the sense that like it has this natural property. But they're often not really like that. Maybe the thing that makes them interesting is the fact that they have a geometric interpretation in terms of bases of some homology group or something, some kind of cycles on something that have some natural, that you would naturally arrive at. Yeah. Yeah, please.
Those integral points, is gamma lambda, are they related to the root lattice of the algebraic substance?
Yes. Yes, they are related to the root lattice. Yes, I'll make that point eventually. Yes, they are. Yeah. So in fact, the root lattice has to do with the first homology of this. Actually, the weight lattice has to do with the first homology of this variety. That's the connection. So, yeah, I'll emphasize this later. But yeah, basically, to each of these points, you can also associate a first homology class on this variety, and there's an identification between the first homology of this variety and the weight lattice. But what's interesting is that that's less refined than this kind of picture that I'm getting. Okay. All right. Okay, so I promised that I would say something about this theory of equivariant Lagrangians. How does this work? So, as I said, this really draws on this work of Seidel and Solomon. In a fundamental way. So, and it also, so it draws on Seidel and Solomon, of course. Okay. And I also, wrote a paper with Yankee developing this in the Lie algebra case. So maybe one way to get into this kind of philosophy is just with something that might be more elementary for if you've studied complex geometry. Might have a complex manifold X and a holomorphic vector bundle E, and then I might have, let's say, a group action on X. Well, I might ask myself, can I make this vector bundle equivariant with respect to this group action? Well, what might you do? Well, one thing you could do is you could sort of differentiate this group action, and one thing you get is that if I have an infinite, a Lie algebra element, what I could do is I could say, well, at that Lie algebra element, let's just say, I can exponentiate it to get a one-parameter subgroup, and then I could pull this vector bundle back under that one-parameter subgroup. And that would give me a continuous family of vector bundles. And I could look at the first order deformation class of that family. So this action will give me a map from G to the space of deformations of E, which we can identify with X1 of EE. Okay. So this is sort of classical Kodaira-style deformation theory that identifies these things. Now, okay, that's good. But now if it was, so this tells us basically when you sort of move the vector bundle by this group action, how does it change? But now if I had an equivariant structure, that means I have a group action up here that commutes. So what that actually means is that when I move the vector bundle by the group action, it's actually isomorphic to itself. And I've chosen an isomorphism. So this equivariant structure is stronger than what I'm about to say, but one thing it gives you is that it trivializes these deformation classes. So if E is equivariant, this deformation is trivialized. Okay, it's not just that it's trivial, but really this lifting of the action is giving you a specific isomorphism between E and its perturbed form. Okay, so if we want to translate to sort of the Fukaya category, so in other words, instead of under mirror symmetry, instead of these vector bundles, or more generally coherent sheaves, I'm considering Lagrangians. So how do I translate to the Fukaya category? Well, this thing that was X1 will become HF1. And I also need an analog of this G business. So right, at this point is where I'm moving to this infinitesimally equivariant. So I'm going to sort of just move to this lowercase g. So this G, right, the big G is an automorphism of X, but the little g is a vector field on X. So this vect X, so this G tainted vect X, this vect X will correspond to, well, okay, what I'll call NC vect, non-commutative vector fields on the Fukaya category. Okay, so what am I calling my manifold? Well, I guess I'm calling it R. Okay, so these vector fields have to be, it's actually a generalization of the concept of vector field, but it's what's called a non-commutative vector field. It's something you can define whenever you have an A infinity category. And what is that? So it's actually it's very simple to define what NC vect is. So the non-commutative vector field in a category, A infinity category A, is just, this is a set. It's a set of closed degree 1 cocycles in the Hochschild complex. Hochschild cochain complex. Okay, so and why is this? I mean, what is the motivation? For this sort of thing. I mean, so if you go back to the algebraic setting, you'll see that there's a theorem, Hochschild-Kostant-Rosenberg theorem, which tells you that polyvector fields on X are going to be isomorphic to the Hochschild cohomology of the coherent sheaves on X. And so, inside here you have vector fields, which is like H0 of the tangent bundle, like global sections of the tangent bundle somehow sits in here. This is isomorphic to this, so it has to sit in here. So we can try to figure out where it is, or we could say, actually, I'll just take all the degree 1 cochains, cocycles. there might be other stuff in here that is not, there might be degree 1 cocycles that don't correspond to vector fields under this isomorphism. Whatever, just take them all. Okay. Right. Why is that? Okay, so that's maybe why that should be a sensible thing to do, is this HKR theorem. But in fact, it actually leads directly to the kind of maps you want, because this cochains, this CC1 of AA, so here I'm using A to denote my A infinity category. One way to present it, so there's, okay, so what do I mean, this cochain complex? Well, there's one specific cochain complex I can use, this bar complex, to compute this. And so this thing will consist of stuff like this. So maybe, okay, maybe I'm going to use notation where I really am thinking about the Fukaya category. So maybe I should write the Fukaya F here. Okay, so this is this thing where you take chains of morphisms. Okay, so one part is this. So for every object I take the degree 1 the degree on endomorphism of that object. Then for every pair of objects K and L, I take actually HOM over my ground field, which I'm just taking to be C, to degree 0 from this thing. To itself, and then times other stuff. So the next one is like homomorphism. So I take a tensor product of 2 morphism spaces here, going to a single morphism space here, and I take the HOM, and then the degree of that HOM would actually be -1. But basically, these are sort of the leading order parts of the Hochschild cochain complex. Leading order in terms of the length of the tensor products that appear inside the term. Okay, so that's good because this, this presentation then gives me a direct connection between these NC vector fields and this kind of thing that I need to connect it to. Okay, so for example, what's the analog of this map from vector fields to deformation space? Well, it's actually just the projection onto this factor. Okay. So if we let C0L equal, so if let's take a C in here, and let's take Psi0L to be, this will be the projection of C to CF1LL. That's the analog of this deformation map. So I think about this psi as a non-commutative vector field. Its projection to CF1 of LL is telling me what's the infinitesimal deformation of L under that vector field. And since it's a cocycle, this is actually a closed element now. That's part of what it means. Okay, but I said I needed to trivialize that deformation class. So the trivialization, which is my equivariant structure, is going to be a choice of, I'll call it CL in CF0LL, such that its differential is this psi L0. Okay, so in other words, I need to trivialize that deformation class. And that choice is what I call an equivariant structure under Lagrangian. Okay, or following Seidel-Solomon. Okay. All right, so good. Questions so far? Let's see. Okay. So what can you do with this? Well, what you'd really like to do is you like to say, okay, maybe this is matching things up. I mean, what does it give you anything concrete? Well, one thing it gives you is when you have 2 equivariant objects, the next thing to study is when you have 2 equivariant objects. So when you have 2 equivariant objects, you can take their HOM, and you would expect there to be a G action on that HOM space. Okay. And that you can also get from here using this next component. So maybe I'll just move that. All right. So now you could consider the next component. So now I could consider C1 KL to be, this is actually the component here. This is actually an endomorphism of the cochain complex for this pair KL. Okay. Yeah. It's not necessarily exact. So, so this is given, and then you want to find this, but neither existence nor uniqueness is true in general. I mean, existence is a condition, and then if it exists, it's not going to be unique. So, yeah. Yeah. But the point is to choose it. It's data. So it's a new piece of data. Just like if I have a nice, just like if you have a vector bundle on, affine space, and you have a group action on affine space, there's many different ways that vector bundle could be made equivariant. Right. More question? Okay. So the next thing you'd like to say is that this thing, this vector, the degree, the sort of length 1 component of this vector field gives you an endomorphism of this space. But that's not, so what actually happens here is that this thing is not necessarily going to be a chain map. So it's an endomorphism of this chain complex, but it doesn't actually commute with the differential. So it doesn't give you a map on homology, but you can correct that using the equivariant structure. So having chosen CK and CL, if they assuming they exist and having chosen them, we can form a map phi, which is going to be the map. It's an endomorphism of this vector space, which sends x to psi KL 1 of x minus mu2 CKX plus mu2 XCL. And this is a chain map. Okay. And so it descends to homology. So that's an interesting action then of this. It's an interesting endomorphism of the cohomology of this thing is an endomorphism of that cohomology group. So that's like a more sort of meaningful thing to calculate because it lives on cohomology level. Okay. But of course, this map depends on, it clearly depends on these choices. Okay. All right. So a couple more things to say about this. Let's see. And I should have 20 minutes left. Okay. Maybe. All right. Maybe a little bit less. Maybe I won't have time necessarily to emphasize this point, but how do you obtain, I said, okay, these NC vector fields are just degree 1 cocycles. How are you ever going to come up with one of those? So fortunately, we have a lot of ways of doing that. So there's a geometric source. Well, there are multiple geometric sources, I would say. One of them is this closed open map. So you have this closed open map from symplectic cohomology. Of course, this is actually defined at the chain level. But the existence of this map tells you that if you want to get a degree 1 element here, you can do it by finding degree 1 elements here. Okay, and so I think this is, I might not talk about these elements much more, but in that big picture I was drawing over here, that's where our things come from. They come from symplectic cohomology. So if you take a degree 1 element, a degree 1 co-cycle in symplectic cohomology and apply this map, you'll get an NC vector field. Okay. All right, and of course this closed open map, this is one of these maps that counts disks sort of with a bunch of boundary inputs on the boundary, an output on the boundary, and an input in the center with a tangent direction. Okay. And maybe just one more remark, which is that this story that I just gave was for a single vector field. So what we actually need to do, though, remember I wanted to get this. So what I actually want is I want to consider a map from G to the symplectic cochain complex of my, I guess it was actually called R. And then I'm going to apply closed open to get to CC1 of the Fukaya category of R. So the story I was sort of presenting so far was just for a single element here. Now I have a positive dimensional subspace of elements, so I have to concern myself with making things compatible. In particular, what you would get is, if you ran the story, basically, if you want to, you could get an endomorphism of this vector space for each element of the Lie algebra independently, but then you have to ask yourself, like, is that map have anything? Is it like a linear map from G to the endomorphisms of the vector space? Is it actually a Lie algebra map? And there are some compatibility conditions that need to be satisfied, but I'm not going to present those right now. They're in the paper with Yankee. Yes? I should not have. This should be R. R. Excuse me. Yes. Let's see, what have I done to confuse you? What was this? This was all in, no, this X is not R. This X is on the, morally speaking, this X is the B side that appears in this line. Everything else, it was supposed to be R, which is ultimately going to be a Weinstein manifold, and the L's and K's are Lagrangians there. Yeah. Yeah, so when I read, so this story is pretty general, so it could be for any of the versions. Ultimately, the category I'm going to consider is a wrapped category. Yeah. Okay, so maybe I'll try to describe. So this is sort of how we get that. This is an explanation of how we get that this bit about the action. Okay, so the problem is actually to build this kind of structure. Okay. So maybe I'll talk about now this Sl3 case. So, and where this basis actually comes from. Okay. So here this G is Sl3. So, and let me maybe say a little bit about what this R actually is. So you can consider a manifold FL3. So this is complete flags in C3. Okay, so it's a line, you have the point, then the line, then a plane containing the line, and then the whole space. Okay. This guy could be written in a certain way, so there's a lot of interesting subvarieties in here. And this can be written this way. So in fact, this FL3, it has a very nice anti-canonical divisor, D, which consists of, I'll just say, a pair of opposite Schubert divisors. Okay, so maybe if you're not familiar with this kind of stuff, this flag variety is a homogeneous variety for this group. But you can get many different cell decompositions of this variety. It actually has a very nice cell structure where all the cells are even dimensional. But you get a different cell decomposition for each. One way to parameterize them is by Borel subgroups of Sl3. So a Borel subgroup is like upper triangular matrices or lower triangular matrices. And so each such decomposition gives you a divisor, which is the complement of the top dimensional stratum. And what this divisor is actually the union of two of those divisors. So you take, say, the divisor for the upper triangular matrices and the divisor for the lower triangular matrices, take their union, and then R is the complement of that. Okay. So R is, so it's nice. R is actually it's the complement of an anti-canonical divisor in FL3. So this R is, a Weinstein manifold. And by now we know a lot about it. So we can prove HMS for this. And the mirror is itself. This is one of these self-mirror situations. That's useful because it means that, okay, I can sort of start interpreting things on the mirror side. Okay, maybe I won't say too much about that right now. Okay. So by the way, about proving HMS, what you can do is, I just wanted to remark, there's a lot of technology for doing this kind of thing now. And this manifold has a pretty simple handle presentation. And so, one way to do this would be, you could use this handle presentation. You can, use, the Lysandrian surgery and the, DGA to calculate Floer cohomology of the cocores. And then, of course, by Yorgos' theorem, we know those cocores generate. And so that calculation tells us what the mirror is. So, in fact, what I'll maybe focus on is that one of the things is you have to calculate some Floer cohomology group to do this, and the way you calculate it, you have to calculate it a certain way to see this canonical basis. Okay. So in fact, this R has a very nice picture. So R admits a Lagrangian torus vibration over, over a base Y. The base Y is just, as a manifold it's R3, but it has an interesting singular affine structure. And what is the singular affine structure? In fact, what Y is it's you have the two-dimensional focus times S1, times R. Okay. So in fact, what you see is you kind of see this picture in 3 dimensions. So what you'll see is a 3-dimensional manifold, and then it has a line in it, which is a line of singularities. That's the discriminant locus. And then the fiber over this discriminant locus looks like a pinch torus cross S1. So the fiber here is going to be this pinch torus times S1. Okay. And then I have to talk about what Lagrangians I'm going to use. So maybe I should explain that a little bit. Yeah. Lagrangian spheres. Yeah, well, there's immersive. Well, no, well, it's 3-dimensional. What do you mean? There's there's Lagrangian S3 and flag 3. How does it look in this picture? Likely. Yeah. Okay. Yeah. So yeah, I could think about that. Yeah. And what are my Lagrangians going to be? What are these L lambdas going to be? Let's see. I mean, so this L lambda, well, remember this L lambda, that's supposed to be this object that corresponds to the representation with highest weight lambda. And what it's actually going to be is it's actually going to be a Lagrangian section with a certain equivariant structure. So here, I don't really have time to, there's a fairly large amount of notation you have to introduce to explain what this equivariant structure is. But basically, yeah, so it's going to be, it's a three-dimensional, it's basically a Lagrangian R3 sitting inside R. You could take, for example, the positive real locus in R in an appropriate coordinate system. And that's going to be a Lagrangian section here. And then there's several different, so that's basically the zero section. That's kind of the thing that's mirror to O. And then there's different things you can do. I could give that different equivariant structures. You could also try things where you move that Lagrangian, you isotope it to a different position. It turns out that it's a little bit difficult to parameterize all the different equivariant objects because there's two things you can do with a Lagrangian. One thing you can do is, if you have an equivariant Lagrangian, that's a pair L and this choice. One thing you can do is change the choice, just to pick a different solution of this equation. The other thing you can do is move the Lagrangian by like a Hamiltonian isotopy. And it turns out that those aren't independent parameters. There's actually a connection between them. So some of this stuff depends somewhat delicately on the perturbations you choose. So you have to pick, you have to cook up a way to parameterize equivariant structures, and I claim that we do. So you can find this equivariant structure that corresponds to this L lambda. Why is that a reasonable thing to do, by the way? Well, one reason why it's a reasonable thing to do is I said that one way you can get representations of a group is you consider line bundles on the flag variety. And now each of these line bundles on the flag variety will correspond to a Lagrangian in the mirror. Okay. Now here I'm sort of, it might get confusing because one of the things that I'm using is that this R is self-mirror. So, but when I think about Lagrangians in this R, those things actually also correspond to line bundles on the mirror, which is also an open set inside the flag variety. And the connection, and that's kind of how the connection works. There's a connection between equivariant line bundles on the flag variety and representations by the Borel-Weber theorem, and I'm applying mirror symmetry to that. Okay. That's why you should expect to get representations from things that look like Lagrangian sections. And so what else? Well, so yes, as I said, you can take these Lagrangians and you can calculate their Floer homology. Like I said, there's, of course, many ways to do that, and you're welcome to use your favorite. Well, yeah, in general, you're welcome to use your favorite way to calculate Floer homology, but if you want to solve the problem I want to solve, you have to do it my way. So basically what we'll do is we'll take, so if I want to calculate this, this wrap Floer homology of H0 of two of these guys, we do this using that's essentially pulled back from Y. So this is this natural thing. You have this completely integrable system. You take a Hamiltonian down, you take a function on the base of the system, you pull it back, that commutes with the, that preserves each of the torus fibers. So it's just a translation along each torus fiber by an amount that depends on where you are in the base. And what you get is that you get a basis. So this thing actually gets a basis maybe I should call it, maybe I should have like P or something, subscript. So gamma P, okay, so P in Y of Z. So in other words, you have this Lagrangian section. This is sort of a standard thing. You have this Lagrangian section. You wrap by a Hamiltonian. You ask, what are the chords? The chords are basically where it's translating each fiber of the integrable system by a certain amount, and basically the chords occur when that translation is 0. And so you find that you get sort of a lattice work. You get a lattice work in this three-dimensional space. Okay. And I call that y of z. So it's like the z points of this integral. It's actually, can be thought of as, this manifold has an atlas where the transition functions are integral affine transformations, and those preserve the condition that the coordinates of a point be integral. So you just take the points with integral coordinates with respect to one or any of the charts in the integral affine atlas. Yes?
Zero is the point that corresponds to a singular fiber. The integral affine structure
You could set, you will have, that's a little bit maybe delicate to say exactly what's going on there. You will have some points that could be near that, yes. But yeah, somehow it still makes sense at those points. Okay, so you get this basis, and gamma sub p is that chord that corresponds to that point. Okay. All right, so you can find now, I guess I'm just going to start asserting things. You can find actually this map. So what I now need, of course, is I need a map from Sl3 to this Sh1 of R. We definitely know, because we know enough mirror symmetry, we definitely know what map we need to take here. You could ask questions about like how geometric can you make this, like how natural is this choice, but you can definitely cook up a map here, and you can cook up these equivariant structures, and you can actually set it up so that this guy does actually contain this V lambda, so that Sl3 will act on this. This is that sort of big picture. This Sl3 will act on this thing will contain that, and this thing will actually be just some subset so P is P in sort of the gamma lambda. Okay. There'll be actually a subset of the integral points that gives you that representation. So in other words, it's interesting when you have a vector space that has a basis, it's interesting that your subspace is given by a subset of the basis. That's that doesn't automatically happen. Okay. Maybe I could just draw a few pictures to show you why this is cool. So, right. So typically, there's one kind of picture you typically draw when you look at SLN representations, which is a weight diagram. So typically it looks something like this. You have this weight lattice, which is this hexagonal lattice, and you might get a weight diagram that looks something like this. Let's see here. This should have been, here. Sorry, okay, 3 there, and then 4, and then this should be 5. And typically it has these kind of like rings of things here. Mm-hmm. So the weight diagram of a representation is often a picture like this. It's drawn in a lattice here. It's drawn in a regular triangular lattice. And then what's interesting is that there's a lot of multiplicities. So this is a weight diagram for a certain representation. So the multiplicities, I think, look like this for this representation. Basically, on the outer ring, all the multiplicities are 1. So all these weight spaces have dimension 1. On this next ring, they all have dimension 2. And then on this next ring, they all have dimension 2. Okay. So this is a very nice picture of the representation. It breaks it up into a lot of different subspaces. So it breaks it up into these weight subspaces. And what you see here, so that's kind of like what we're doing with this canonical basis, except you have this degeneracy. Right? Some of these spaces are not one-dimensional, they're two-dimensional. Or in general, as you go to more complicated representations, you have any dimension of weight space. But what's interesting is that in this picture, sort of you see a collection of points where each space is one-dimensional. So there's like a one-dimensional space attached to each point. And basically what's happening is that, this picture is two-dimensional because the rank of SL3 is 2. But that picture is three-dimensional because the base of the XYZ vibration has 3 dimensions. And so that's why you're able to refine things more. So in fact, this picture arises, as I said in response to a question earlier, this picture arises because the first homology of this R is the weight lattice. It is the weight lattice. And so if you take each of these generators, they're actually represented, they can be represented by loops in R, and you project them to this, you actually will get this diagram. So you take these basis elements, you project them to H1 of R, you get this weight diagram. But when you think of them as sitting in the base of the SYZ vibration, you sort of see a three-dimensional picture where they fill out the integral points of what I would call a polytope, except it's a polytope that lives in a singular affine manifold. A normal polytope lives in Rn, but here it's like a polytope inside the singular affine manifold. Okay. So I think in the interest of time, I'll stop there, and if you have more questions, please talk to me. Okay, thank you.